Let's begin by taking a look where we left off yesterday. Okay, so we'll start with this last example. We quickly listed the formula, and that's the last part we got to. Okay, that's where we left off. And the problem asks us, when a car is moving around a circular track, we're told that the radius of the track is 20 meters, and the centripetal acceleration is 6 meters per second squared. Simply find the speed of the car. Now, remember, first of all, think about a diagram in your head. Here's a circular track. There's a car moving around the track. Here's the center of the track. Here's the radius. The radius length is, oops, not 5, but 20 meters. Okay? Remember, the acceleration is centripetal. Remember, centripetal means center seeking. So if we wanted to draw our acceleration is aimed toward the center always. So if the track or the person is on the track and the car right here, that's what our diagram would look like. But if the car was at the top of the track or another spot on the track, now the acceleration is aimed toward the center this way. So remember that the acceleration, its direction changes. It's always toward the center. And that's what we did yesterday with that cup of water. When we had the rope or the cord had enough tension in it to pull that cup back toward the middle. It prevented it from flying off. Okay? Now, we're looking for the speed in this problem. And it's not going to always say find the tangential speed, even though that's what we're finding. You need to use your intuition and see, okay, this is circular motion. Circular motion has tangential speed. So even though it just says what is the speed of the car, we know right away that because it's in circular motion, we are looking for the tangential speed, Vt. We were starting this one. The 2R, the 3R, we started this one. All right. The outside person. Like we said, the inside person takes the short path, the middle person takes the medium path, the outside person takes the longer path. So because, no, we didn't. It was just conceptual. Yeah. So the outer person is to travel the furthest distance in the same amount of time. So let's solve for Vt. Move the R up, please. No number, just variables first. Move the R up. Focus, gentlemen, come on.
Vt equals square root of ACR.
Okay? So the square root of AC times R. The square root of AC times R is Vt. What do you get for a number?
I got Vt equals 10.954.
10.954?
Yeah. Because AC times R is 120.
945. Or 954. Yeah. Yeah, 954. Okay, what about units?
Meters.
Per second. Again, what is this? This is the speed. Remember, speed and velocity are measured in length over time. Meters per second. Okay? Okay, on this one so far? All right. Fernando asked me something before class. Remember, guys, at the bottom of your notes, I always put a bunch of sample problems for you to work on for homework. Okay, so feel free to look at them. And if you tried them last night, the first 2 or so, you would have probably been able to do, but we didn't get to the last one yet. So now we're going to start the next thing, which will cover that section. Okay? All right, so here we go. Let's begin. Next one, centripetal force. Remember, what is holding that cup of water in motion was the string, right? And there was tension in the string. So there was a force of tension pulling the cup of water back toward the middle. If that force of tension hadn't been there, the cup of water would just fly off. So there's got to be a force. So whenever you have something moving in circular motion, not only do you have the acceleration acting toward the middle, you also have a force acting toward the middle. That's a comma in between them. You have a force acting toward the middle. And we remember Newton's laws tell us F equals ma. Instead of F equals ma, we'll write it as the force of centripetal equals the mass times the centripetal acceleration. So I haven't changed anything, but instead of just looking at linear forces like we talked about all year, the force on a car moving forward, or the force of friction resisting motion. Now we're looking at a centripetal force. So instead of just having acceleration, now we have a centripetal acceleration. But from last class, we defined centripetal acceleration as Vt squared over r. So simply replace this, replace AC with Vt squared over r, and this is what you'll end up getting. Okay? Again, on your test, to give you a little preview so you have an idea, you're going to be given the formula, and you can look at the updated formula sheet on Moodle or the documents and handouts. But you'll be given this formula, okay, on the test. You're not going to be given this one that I just boxed in. But you should be able to get that formula just by thinking about F equals ma. If you know F equals ma, which is on your formula sheet already, and you know this formula right here, you simply plug in for A, and this is what you end up getting. Are we all clear as to what I'm saying right now? Sure. So again, you're not going to be given the formula that's boxed in here, but you do know F equals ma, and you know that the acceleration is Vt squared over r. So go ahead and substitute in when you're on the test, and you'll derive the other formula. Okay? Now, with that said, let's go ahead and look at some examples. Before we get to numerical examples, let's think about some conceptual ones. First, we talked about the cup of water swinging around, and the force of tension held it in motion. What did we say keeps a car in motion when it goes in a circle? What keeps it in that circular motion? Prevents it from like slipping out or sliding across the road? Force of friction. Very good, Jeff. Force of friction. So let's go ahead and look at a bunch of examples now. Okay, we're going to fill in this table. Just so we're clear conceptually as to what holds things in motion. And then we'll get to some numerical examples. Okay, take a minute to write them down. We're going to look at 6 different scenarios, and we already did the first 2. Okay, the first one we said was the force of tension. That was the cup of water being held by a rope or by a string. The second one we talked about the force of friction. Now, for a lot of these, there are other forces that are playing a part as well, but I'm listing the major things. So like, for a car around a track, it's friction, but it's also the actual force of the car's engine or the thrust of the actual car itself. Okay? So there's going to be other stuff, but I'm listing the major things. Sasha, would you go back to the last slide? I'm not done with this one. Here, you know what? I'm not done with this one. Well, I'm not done with the last slide.
You know what? I'll work these documents.
I've lost it.
Wait, so where she gets the midterm, right?
This is the last topic on the video. This is the last thing, yeah? And this is also the last thing on your test. If you're going to see these homework problems already.
I forgot we have 6 too.
6263, and then 7263.
No, no, they can't.
So much in the problem, just do
Yeah,
mine.
that's that.
What was your
I
problem?
mean, but like, I'm talking about like just like not doing it.
Okay, third one.
Just straight up all.
The roller coaster in a loop-the-loop. What actually keeps that in motion? This is tough. This is what a lot of people have trouble with. And think about this for a second. If you have enough speed, it'll keep it in motion, but we're looking for a force, remember. We're looking at the centripetal force is provided by what? So it needs to be like friction force or tension force. We need an actual force.
Normal
Normal
force?
force. Well done. Normal force. Okay, and think about it for a second. If the car, and I'm going to draw a little diagram. Okay, here's the car of the roller coaster here at this point. What's keeping it from falling through the ground? Normal force. That's obvious here. But it becomes difficult for a lot of students when it gets to this point. Well, what's keeping this roller coaster from flying off this way? The normal force is pushing back from the track. Again, it wants to just keep going off, but the normal force is keeping it in motion because the track is pushing back against it. So this is the normal force. Okay, the normal force. Next, a stunt devil airplane. A stunt devil airplane. Little tricky one also. And these might be forces that we haven't used as terms before, so give me an idea of what you think it might be, and I'll give you the right term for the force.
What has something to do with like tangential speed?
There's tangential speed in the problem, but I'm looking for the force that's keeping it in motion, Paul. I mean actual like force itself. Speed is like a velocity or a rate.
Centripetal acceleration.
right? So gravitational force is part of it, but there's there's other forces that are more apparent in this part.
Wouldn't it be like friction when it goes up, like the flaps on the plane?
So what do we call that for planes? It is a type of friction, absolutely, but there's a specific term for when it's a plane or a car traveling in air resistance. What do we call that?
Aerodynamic friction?
Air resistance is a good way to think about aerodynamic friction. Drag force. Drag is the terminology, okay? Now, listen, there's another force that keeps it in motion, especially when the airplane starts to flip. So imagine how this is an airplane over here, okay? As soon as the airplane starts to lift up and it starts to flip, and then it starts to loop back around. But to get it to actually move up, what's the other force that we have involved here?
Like the engine?
The engine itself, definitely, the engine involved. But I want to know, like, physically, what's pushing it upward? What's pushing it upward? The drag is kind of keeping it stable, but there's something else that's pushing it upward at first. The air, okay, but anybody know what the term is for this one? You're right, it is the air, for sure. But it is the air under the wing as opposed to the air above the wing. And we call it something else. I'm trying to see if we know these terms, maybe. What is it? Not draft, but I can see why you're thinking draft, because it has to do with airflow. Tosh? Lift. Good, lift. Lift and drag. Lift and drag. So, lift is what causes the airplane to actually take off. Drag is what helps it actually come back down. So in this motion, when an airplane does this, it's going to have lift and drag forces. You're all right in the things you're saying. That's what I'm trying to explain. So air resistance I heard draft. How's that? But we're going to call these lift and drag forces. All right. The electron in orbit. So, you have an electron that's hypothetically revolving around a nucleus, even though we know they don't actually revolve now. It's a new, thing in nuclear physics. What's keeping it in motion?
Wouldn't it be like the force or whatever?
Okay, I could see it called an orbital force, sure, but there's an actual type, a name for this. Not gravitational, this stuff. Other stuff that keeps in orbit like a planet. So, why don't you answer the last one for us, Olivier? What's the last one? Yeah, the last one is gravitational. A satellite or a moon around the Earth, the gravity is keeping it in orbit. So here, let's answer that one, because that is gravitational force.
Isn't there no gravity in space?
There is gravity, it's just that when two objects are so far apart, it doesn't really feel the force. It's the distance. And you know what? To answer that question, we'll wait until we get to the next thing in this. We're going to talk about gravitational force and how the distance between them impacts it. And when the distance is large enough, you don't feel it, even though it is there. Okay?
Why is the orbit in quotations?
Because an electron really doesn't orbit the nucleus. That was the original model. That was one of the models, like Bohr's model or Rutherford's model we talk about. One of the original models that actually orbits. But we learn now in a lot of quantum mechanics that the location is based on actually probability. And it's a little bit different. I'm not going to get into it right now, but that's why I put a quote around orbit. I know you know. Hold on one second. Electron. What is the charge on electrons?
Negative.
What's the charge on a nucleus? It's actually positive because there's neutrons, but there's also protons. The neutrons keep the nucleus neutral, but the abundance of protons make it an overall positive.
So it's a magnetic force.
Yes. So we call it electrostatic or electromagnetic force. Okay? Electrostatic is the actual term, but if you want to say electromagnetic, it's fine. Because you think of magnets as positive and negative.
When you think of those, do you know those globes you have on the stand that spin around? No, they're just like air.
Oh yeah, there's like floating globe thing.
Yeah, the floating globe thing.
I've never seen it before.
Really?
You might be going on the quantum study, and then like each little stand, a globe that spins around, there's like space between the top and the bottom of the magnet.
Oh, I actually do. When I was in high school, a student in my class, or a classmate of mine brought that in. And it looks like it's floating, but there's really a positive and negative charge, and it's keeping it in space. Yeah, that's like the electrostatic force in a sense, because that's electromagnetic. It's keeping it. Yeah. The idea is this, though. Here's this. The whole idea of this is to summarize. Centripetal force is a theory or an entity, but it's not always the same thing. So when I spin something on a rope, it's tension. When it's something revolving around a planet, it's gravity. So the centripetal force is provided by different things based on the scenario. Is that clear? You can expect this to be a short answer. I'll tell you right now in the test on Friday. Maybe give 3 examples of centripetal force and 3 situations. Okay? I'm telling you now that you can expect it. Or maybe a multiple choice. Which of the 4 examples here might not be centripetal force, or an example of centripetal force? Okay? So this is a theoretical kind of problem, but it's good to know that it's provided by different things depending on the scenario. Okay, depending on the scenario. Let's go to an example problem now. During Project Adventure, have you ever done a Project Adventure before?
Nah, like.
It's when you're on like a team, and you have to like move from island to island, and you can't like, you have to like climb ropes and swim across things and go on carts, and you have to work as a team to move people around spots.
It's like Wipeout.
Yeah,
No, yeah. No, I know what you're talking about.
It's like reality TV
No,
shows.
yeah.
It's like reality TV shows.
Yeah, that's what he's talking about. You have to like jump from one thing to the other, and you have to like run under a spinning wheel at the right time.
I get what you're talking
So,
about.
during Project Adventure,
Nobody gets it.
you have to swing on a rope to move between 2 islands. Okay? So what I think about right away is a pendulum, actually. Because think about a person on a rope swinging. Isn't that a pendulum? Okay? That's really what it is. That's what we model things. Remember physics, you model? So if I were to model this scenario, I would think of a pendulum in this case. Now, if your mass is 60 kilograms, the length of the rope is 8 meters, and the rope can withstand a force of 100 newtons, then what's the maximum speed with which you can swing? Okay, and what is the maximum speed with which you can swing? And I actually thought about this problem because if you think about it, if a rope is not strong enough, it's going to snap, right? It's going to break, it's going to exceed the tension in the rope. Or the tension in the rope will exceed its allowable force. So we want to make sure here that we figure out what the speed is so that the person doesn't actually break the rope in half. Okay, or snap the rope. Now, what I want to do is start by drawing a diagram first. Okay, so start by drawing a diagram, please. Here's like the person beforehand. And they say their hands are on the rope and they're about to swing. Okay? The person swings through this path from one island or one object to the other island. Agreed? Does that make sense, the diagram? Now, here's the key. This is where you have to use your imagination. This is circular motion. And a lot of people forget that it's circular motion. Because if you continue the path indefinitely, it will come back around and make a circle. It'll go off the page, it'll come off the page here, and eventually this path will come back around and make a circle. And clearly there's a ceiling here, so I know that you guys can tell that the person is not really going to make a circle if they can't go through the ceiling. But if you think about it conceptually, it is a circular path. Whenever something moves on an arc, so a roller coaster, if a roller coaster does this, right? Watch my hand. Say a roller coaster just comes up to the top, goes back down, and just moves like this. And then it keeps going. It did make a circle, but that is circular motion because it's taking some curved path. So whenever you see some sort of an arc, think of circular motion. Okay, again, when you see a curved path like an arc, think of circular motion. Now, with that said, let's label what we know. The length of the rope is? So what is that in the case of the circle? The radius. Think about the circle. Here's the circle right here. Here's 8 meters. That's the length of this rope right here. Well, that's the radius of the circle. So let's start by writing the radius is 8 meters. And that's why this is a little bit tricky, because the problem does not tell you the radius is 8. It tells you the length of the rope is 8. But if you know the length of the rope is the radius, then you're good to go. Next, you're told the mass, so just list that, please. You're told the maximum force that the rope can withstand is 100 newtons. So what would I call this? Instead of just F. For max, you mean? Okay, well, you will use an M, but before the M, what kind of force is this? Centripetal. So we call it FC, and then we can put a little max down here.
Yeah, that's not fair.
You're in so much trouble, guys. I can't believe it.
Wait, that's not fair.
Hurry back, please.
What if they actually are in big trouble and then you just been like,
Give me an English textbook.
I'm gonna miss grab your locker. Grab your locker, we getting stuff. Wait, that's actually not fair.
Okay, now. So we'll call it FC, and as Garrett said, let's call it FC max to indicate that this is the force of centrifugal motion, but it's the maximum allowable value of the rope. What happens if the person swings too fast? What'll happen to the rope? It'll break. The rope will break. And again, what are we finding? We're finding the maximum speed. So we're finding VT max. Okay, so let's list our formula now. From the last section, we said, well, okay, we remember that the centripetal acceleration is VT squared over R. So the force of centripetal is m VT squared over R. Remember, you're always given this one right here, but you're not necessarily using it. You're just plugging it in for the acceleration in F equals ma. So instead of FC, we called it FC max. So let's write a little max down here. And by default, VT is VT max. It doesn't matter. You don't have to call it max if you don't want to. Okay, but it is max. Right, Max? It was really bad.
No, my face.
Your name is Max. So.
Face. Oh, you get expelled.
Okay. The ball. So.
And no one laughed for Jack.
Where's my book?
If we're given, Jess.
Did they find the cocaine?
If we're given, FC Max, not a good joke, guys. Not a good joke that time.
Yeah, that was a little.
The line was here. You went way too far.
I've gone way far.
I know you have, but for this situation, too
One
far.
time I mentioned acid in a
Now.
class, and the teacher had to report it, and I had to like go.
You mean like an acid or a base, right?
I was like, I guess my.
FC Max.
I was saying that the joke was
FC Max is given. We're trying to find VT here. We're trying to find VT. Now, solve it just as if you solved the last one, please. Move over the R, take the R, multiply it, take the M, divide, and then take the square root. So again, we're trying to find the maximum speed allowable for the person because we know the maximum force allowable. So the only thing we're looking for is VT. So again, this becomes...
Just to make sure to get from AC to FC, we had to put the m in front of VT squared because F equals ma.
Exactly. That's exactly right. And you, Gary, you can memorize this formula, F equals mv squared over R. And when I was in high school in physics, because I used it so often, I ended up memorizing it inherently. But you can always just say, well, F equals ma, plug it in for A, and that's what you're getting. Okay? So let's go ahead and do this.
Square root.
What happens to the A though?
What happened to A? Well, if you remember, Jeff, okay, F equals ma, we take this quantity, plug it in there for A, and that's the equation we get. Okay, so again, you're always going to be given this on your test. You have to remember F equals ma, so if you want centripetal force, you just plug in centripetal acceleration in for A, and that's what you end up getting from that. It's like a substitution or a combination.
C is centripetal.
Yes, centripetal.
Same thing as AC.
It's similar, it just has an M in front of it. See the difference? Same formula, but there's an M in front.
Why can you say that the rope won't work if we choose?
Okay, let's discuss this. Let's talk. We're going to find an answer right now that's a certain velocity, right? Now, the number we end up getting, what do you guys get? I got 3.65. Yeah, 3.65. And let's talk about this now. So if you think about this, that's in meters per second, because it's velocity. Oops, let's go back. Hold on. Okay, so if we think about this now, look at your answer. The reason this is the maximum allowable velocity is because if you think about it and you increase this number, look at your equation over here now. If you increase V, it's going to make this number increase. If you have, say this is like, say this were 10, and this were 5, and this were 5, and then you squared it. Instead of the 5 here, make believe this were now 8. If you make this number bigger, it's going to make the force bigger, right? So if you increase this value, it's going to make the force go above 1,000. But we were told in the problem that the maximum, I'm sorry, 100, let me correct myself. We were told that the maximum force the rope can withstand is 100. So if you pick any value for Vt bigger than this, it's going to make Fc get bigger than 100, which causes the rope to snap. Okay? Which causes the rope to snap. So again, 3.65 for a velocity, 60 for a mass, 8 for a radius gives you exactly 100. Anything bigger in a velocity, any velocity bigger, plug in 3.66, okay? It's going to make the centrifugal force bigger than 100, but we're told that it can only be 100. If that happened, the rope would snap, okay? So this is the maximum allowable velocity of the object or the person.
Wait, but 8 was what we used for the R, correct?
Say again?
For the R, the radius.
It was 8. And that was the length of the rope. Because we looked at the diagram we drew, and we saw that the length of the rope really represented the radius of the circle. Okay, 'cause this is really a circle here, and that's like the radius.
You said if the speed or the radius is higher than the mass.
No, the velocity.
Oh, velocity.
The velocity exceeds that, okay? All right, now, the last example in that table that we made earlier, the last example was an object in orbit around a planet. We're going to study that right now. We're going to look at that, look at the forces on it, okay? We're going to think about what causes an attraction between two objects in space. What causes the moon to stay in orbit, and that's gravity. And what we're going to do is we're going to look at the force of gravity. So let's start by just simply writing this down. So the gravitational force is defined as the mutual force of attraction between two particles of matter. A particle of matter could be, an atom. A particle of matter could simply be something like, the Earth. You could model anything as particles. So the force of attraction, that mutual force between the two, is the force of gravity. Now, on Earth, we know force of gravity is equal to mg. Right? We say Fg equals mg, and we've said that many times. But this is our governing law right here. Okay, that's our governing law we're going to look at, where now g is a different value. This is capital G. If you want to write this down, this is called the universal gravitational constant. Gravitational constant. It is. The universal gravitational constant. This number is an empirical value that scientists measure, but it does not change in the universe. So this G is the same G everywhere, whereas the last G, if you remember, is only for Earth. Remember 9.81? That was Earth. Whereas the Moon was 1/6 of that. Whereas Jupiter is around 25.9. So that little g, that value little g, is specific to each planet. It's specific to each body of mass. This big G is a constant that is the same throughout the universe. Okay? And if we have time at the end of today, we can derive or show where little g comes from using this big G, actually. We can determine where 9.81 comes from using this value.
What are the subscripts to the M?
M1 and M2 are the two masses, or the two particles that are separated. Okay? So M1 and M2 over R squared.
Like the ground and the person.
Or like the Earth and the person. You need the whole object itself. So like, if I look at these two chairs, you don't see them pulling each other together, but they are, believe it or not. But the force is so small that it's negligible. Again, any two objects are pulling each other together. This scissor is pulling this piece of paper toward it. This chair is pulling this desk. This chair is pulling the room, is pulling the light fixtures. But the forces are so small that you don't notice them. But if you want to use gentlemen, if you want a pickup line, gravity is pulling me towards you. It literally is. It really is pulling things together. The force is so little that it's negligible. You don't notice it. Okay? You really don't notice it. Now, and let's think about this. Earth is able to because the mass of the Earth is so tremendous that this M1 value for the Earth, and say M2 is, me or some object on the Earth, this room, the mass of the Earth is so large that it makes the numerator so big, which makes the force of gravity something that you can actually feel. Whereas the mass of this thing, this remote, and the mass of this paper, they are so small on a relative scale. The mass of these objects is tiny, that you don't feel the force of gravity between them, even though it does exist. Okay? It does exist. Now, R, in this case, please write this down, see in parentheses. R is not the radius in this case. R is the distance between the centers of the objects. The distance from center to center. And that's R squared in the denominator. Okay, again, R is the distance from center to center. So to make it clear as to what I'm talking about, if this is the Earth and this is the Moon, the distance between them, R, is not this gap. This is not R. R is from the center to the center. So R would be like the radius of the Earth plus the gap in space plus the radius of the Moon.
How do you find out the first? And I can calculate.
I was about to ask.
Everyone has a center, actually. Everyone has a center of mass. There is a spot in your body that is the center of mass. It's called the centroid. And there is a location. And you can calculate it. There are ways to calculate it. It's a lot more difficult than what we're going to do. But you do have a center. You would almost ignore your center because, think about it. If you were thinking about the distance between you and the Earth's center, here's the Earth right here. Look at the radius of the Earth. It's very, very tremendous, the radius of the Earth. The distance between your center of your body and the ground is so small relative to the radius of the Earth that you don't even consider it. So if you're looking at yourself, you pretty much think about the radius of the Earth. But because we're talking about objects in orbit, we have to consider the fact that this is R. This full distance is R. So for a problem like this, for the Moon and the Earth, the distance R is equal to the radius of the Earth plus the gap, I'll call that D, that distance here, plus the radius of the Moon. That's what little r is in this equation now. Again, this is RE, this is RM, but the whole R is the sum. It's the segment addition postulate from geometry last year. If you add three segments together, you get the major segment. Adding RE, D, and RM, this is RM, just to be clear, that's RM over there. The sum of those three numbers is the distance from center to center. So for a problem like this, you would need a table of values, and your book gives you these values. On the test, I will give you the values. So you'll be told the radius of the Earth is x, or whatever it is. The distance between the Earth and the Moon is this value. The radius of the Moon is this value. Find the gravitational force between the two. You need to know to add those three values together, and that's what R is, which is what goes in that equation right there. Okay, Jack?
Well, I don't know if it matters or not, but how do you know which is RE and RM?
E just stands for Earth, M stands for Moon. I'm just giving subscripts for the names, yeah.
Okay, yeah.
You can call R1, you can call this here in the middle R2, call this R3, as long as you know to add them together.
Yeah, so you're in this chart.
Nice and active, so to speak.
In the chart we did before, the force friction and all the different types of forces, each one has its own equation. We have to know that in
No, all you need to know is centripetal force in general, and then the gravitational is the only one we're going to look at. We're not going to go into details about drag force and lift force. A lot of them involve differential equations and calculus. So to study those, you can take courses on their own just on those topics alone. So we're just looking specifically at the last example from that table. That's the only one we're going to really look at. But yes, Jeff, a lot of them do have different values. Let's look at an example now. Let's take a look at an example. Two dump trucks of equal mass experience a gravitational force between them of 4 times 10 to the negative 5 newtons. A very small value, right? 0.00004. Very small value. If they are 5 meters apart, and I'm telling you center to center, I'm telling you the distance between their centers is 5 meters. So it's like, here's truck 1. Here's truck 2. And here's the center of this one, and here's the center of this one, I'm actually giving you the center to center distance. So you don't have to worry about adding in like a radius this time. Okay? So again, in this problem you're told the distance between center to center is 5. You're told that the force that they exhibit is 4 times 10 to the negative 5 newtons, and we want to determine their masses. Okay? So start with your equation, which by the way, you're going to be given the equation and you're going to be given capital G. You don't have to memorize those. Please make sure you look at the cumulative formula sheet on your documents and handouts, please, before this test, so you know what you should expect on the test. Okay? So you're given this formula on the test. I'll write it down for now, but you'll be given this. Okay? Let's list our givens. What are some givens in this problem here?
We got the
We got the R,
R.
good, and that is? Good. What's FG? Good, and I'm going to write it just to make it easier on us all. Okay, 0.0004, and that's newtons. Again, remember scientific notation, -5 means move it 5 spots to the left, the decimal. What else do I know? I know capital G, even though I don't have it memorized maybe, but I do know, and here's how I remember, it kind of rhymes. 6, 6, 7, 10 to the negative 11. 6, 6, 7, 10 to the negative 11. And remember there's a decimal. Okay, and it's scientific notation, so which tells you the decimal has to be here. 6, 6, 7, 10 to the negative 11. Okay, give yourself little, mnemonics to help you memorize. And the units, which I honestly don't even memorize half the time, the units of it. Units are.
I thought you said you give us G.
You do. I'm just telling you in case you want to have a way of memorizing, in case you like the units.
That gravitational force and like 9.81.
9.81 is Earth's gravitational constant. This is the gravitational constant for the universe. And it's a different formula, clearly. Remember Earth was this?
So we have like,
Okay, that was Earth.
Yeah, but why are we trying to find out two?
It's different. And if we have time, I'll go into more of it. But for now, I'm going to stop because we're going to run out of time right now.
in my head I can just pretend like that's just
It's different things. This is specific to Earth. This is anywhere in the universe. We happen to be given a distance between them, so we're going to use this formula. Okay? Now, we're told that the dump trucks are what? Equal mass. So instead of M1 and M2, what should I just call each of them? Yeah, just call each of them M. So this equation simplifies a little bit. Again, we know that the dump trucks are equal mass, so write this, please. Okay? It's really M times M. M1 and M2 are both M. So if M times M, you just write M squared. And what are we solving for? We're solving for the mass. Let's move R squared up over the left side of the equation. So I'll take R squared and move it up. Okay, take the R squared and move it up. Divide by G. Remember, F little g is not F times g. Fg is its entity itself. This is the gravitational force. So don't try and cancel the g's here. I've had students that cancel these g's. That is not a variable, that little g. That just means the force of gravity. And now that equals m squared, so I should take the square root, right? Okay, so to get rid of the square here, take the square root. What we're going to get as an answer is 3,872, and the units are mass. So what are the units of mass? Kilograms. Okay, kilograms. You really, really, really need to practice this because you know what? This is not easy to put in your calculator always. It's scientific notation. You have to plug in 6.67 times 10 to the negative 11. So make sure you're practicing this on your own. Okay, when you work on these problems for homework and stuff, when you're working on them, actually go through the numbers, plug them in. Don't just get the algebraic solution and then look at the answer in the back. You can check the answer in the back, but actually go through this process, please. Okay, because a lot of students have trouble with this.
it's 3,871.
I got 3872. I don't know, it might be 3871, maybe rounded. Don't worry, but it should be fine. I want to do one more problem to end the day. One more problem, and this is conceptual, this problem here. This is the kind of problem you can definitely expect on a multiple choice. I'm telling you now. Okay, you can definitely expect this kind of problem for multiple choice. What happens to the force of gravity between two objects if the distance between their centers is doubled? Let's start by writing our formula. What variable is changing in this problem? Please tell me. What variable on the right-hand side of the equation, G, M1, M2, or R, is changing based on the explanation of this problem? What is it? R. Very good. M is not changing. The masses aren't changing. The gravitational constant is hence a constant, so it's not changing. R is what's changing. What's happening to R, Dan? It's being doubled. So instead of R, what should I put? 2R. Or that, yeah, I like the diameter. But let's just put 2R for now. The diameter does work.
I like that.
So let's write this. Rewrite the formula the same way. But instead put 2R. Because now R, instead of being, let's say R was 5, and you were to do 5 squared, what would the denominator become if it was 5? The denominator would be 25. Everybody agree with that? If the radius was 5, if the distance was 5. But now if the distance was double that, what's double 5, everybody? And then 10 squared is? So look at your denominator. What did the denominator go up by? A factor of? 4. So that means that we're dividing by something that's 4 times as big. So the gravitational force, Fg, reduces by a factor of 4. Why does it reduce? Because it's in the denominator that changed. Remember, think about it. If I have $20 and I split it between me and Jeff, we have $10 each. But if I split it between 4 of us, now we have only $5 each. So if the denominator gets bigger, your answer has to go down. Okay? There are a bunch of homework problems on Moodle. At the end of your notes, they're they're listed right here. You can write them now, or you can just look at Moodle. Okay, they're on the notes. The denominator gets bigger. Have a nice day, Molly. Wow.
Just call me Holly.
Yeah, I'm sorry.